say that you're asked to take care of a bunch of kids, and maybe it's for the whole afternoon, and these kids look really sweet, but for hour after hour, things are eventually going to devolve and get out of control. And one of the techniques for managing a bunch of kids as soon as things get out of control is totally separating them, right? Like you to that room, you to this room, you to this room, all of them. As long as you can separate them, then you can kind of control the chaos. So this is the thinking, the idea behind our next method of integration, which is integration by partial fractions. This is where we're going to take something complicated, somewhat chaotic maybe, and split it apart, and it'll become easier. So say that we were asked to integrate this integrand here, and none of the methods that we've looked at so far are going to work. You can't use substitution because this is not a function derivative pair here, and integration by parts is not going to work. So we're going to use a method called partial fractions, and this is actually going to become equal to the sum of two simpler integrals. It'll look like this. So we're going to take something that's somewhat complicated and split it up into simpler pairs that we can manage, that we can kind of take control of and know how to find the integral for. And one big question is, why are these equal? Like, how did we do this? This is actually a method that technically is learned in earlier algebra classes, this idea of decomposition by partial fractions. It's not like completely used everyday type stuff, so we're going to review it a little bit. But the idea is we're going to take this initial polynomial over a polynomial, it's a rational function, and split it up into sort of simpler and easier integrals. Both of these integrals, you're going to get to the point where you can just do it by looking at these. These are, you could use a use substitution on each of these, or you can essentially after a little practice, you'll just just look at it and know what the integral is. So the real question we want to answer is how. How is this equal, and how is this done? How do we find these partial fractions ourselves? So partial fractions will work when you have a polynomial over another polynomial. So these are both polynomials. And the degree of the polynomial in the numerator on the top has to be less than the degree of the polynomial on the bottom, or the numerator. And if it's not, there's ways to make it so that you find a degree polynomial smaller than on the numerator than the denominator. So if both of these conditions are met, where you have a polynomial over another polynomial and the degree of the top is less than the degree of the bottom, then you can do this method of partial fractions, where we take this and separate it into smaller or simpler fractions. This one does work. This is a polynomial. This is a polynomial. The degree of this polynomial, the highest degree is 1, and the highest degree of this polynomial is 2. So this one does qualify. It's smaller. So because of that, we'll be able to write this guy as the sum of simpler fractions. You've probably seen this method before, but we'll review it. Essentially, this section is kind of weighted a little bit funny, because if you think of all of the learning that we're going to do in this integration by partial fractions, our efforts here are not really spent a lot in the integral itself. It's just getting it ready for the integral. So our efforts here will be pretty much, first we have to decide, let's see, our first task is do partial fractions apply. After we've answered this question, then we actually spend quite a bit of time finding the partial fraction decomposition, something like maybe this amount of time. So actually figuring out the partial fractions. This is just algebra. Once we figure out the partial fractions, the actual calculus, the integration, is fairly simple. So we spend a little bit of time then integrating. So we got to figure out, well, this one's pretty easy. These are the only two conditions here. And then this one is kind of where the bulk of the work in these problems is done, is figuring out the actual partial function decomposition. The integration is usually just a slam dunk after that. So before we go any further, I just want to kind of stress, when does it apply, when does it doesn't. Which of these will it apply to both of these integrals? None of them, one of them. So let's take a look at this one. This is a polynomial over a polynomial, and the degree of this polynomial is smaller than the degree of this polynomial, so this is a big yes, it applies here. So this is yes. And then we suspect that maybe this is a problem. Why doesn't partial fractions work in this case? Well, the denominator definitely has a polynomial, but the numerator, this is not a polynomial. It's got this square root. If it didn't have the square root, it would be fine, but this totally kicks it out of the class of polynomials. So this one is a big no. The top is not a polynomial. So the first example we're going to try is this guy right here, and we're going to answer the question, does integration by parts even apply here? And I myself just made one of the most common error. We're not doing integration by parts, we're doing integration by partial fractions. And because the names are so similar, I misspoke. This is a very different process than integration by parts, but I want to ask ourselves, does integration by partial fractions apply? And remember, the two conditions have to be met. And the two conditions are that we have a polynomial over a polynomial. We've already established, because this is actually the example from the first page, that this is a polynomial and this is a polynomial. So we're good to go on that count. That looks good. And then the second requirement is, does the degree of the top, is it less than the degree of the bottom? This is degree 1, this is degree 2, so we're good there too. Okay, so now we're going to take a fair amount of time. All of this space here is going to be finding the actual partial fraction decomposition, and then we're going to take an itty-bitty amount of space here to do the integration. So integration, partial fraction decomposition. So this is how the partial fraction decomposition is going to work. We are given 5x plus 4 over all of this, but this is really, I know I can factor it into two binomials. X, let's see, plus 2 minus 1 is how it should factor. And so I have x plus 2 times x minus 1. From a theorem in algebra, we know that this will be equal to some number a over x plus 2 plus another number b over x minus 1, and our only task is to find a and b. So what we're going to do is multiply both sides by this. We'll multiply it over here and over here. It basically cancels right there. So we're left with 5x plus 4 equals a times x minus 1. We multiplied this guy by a, but the x plus 2's cancel, so I have a times x minus 1, and then I have plus b times x plus 2. So again, all I did going from here to here is I multiplied both sides by x plus 2 times x minus 1. It canceled here, and then certain things canceled on the right side, but other parts of that product were left behind. Okay, and I'm going to spread everything out, and then basically I'm going to collect my x terms on the left and the right, and they'll have to be equal, and then I'm going to collect my constant terms on the left and on the right, and they will also have to be equal. So I have 5x plus 4 5x plus 4 equals a, x minus a plus b, x plus 2b. This equals a plus b times x plus a negative a plus 2b. And this part on the left side is staying the same. So I've expanded everything out, and then I collected any term that had an x in it right here and kind of factored out the a plus b. And then I collected any constant term and put those together. So because of this equality, and there's a 5x over here, so any of the x terms have to be equal to that. So 5 must be equal to a plus b. And then with similar logic, this constant 4 has to be equal to whatever constants are left behind. So 4 equals negative a plus 2b. At this point, we just have a system of equations. And this one is a pretty easy one to solve. We can just add straight down because that will eliminate the a's, and we have 9 equals 3b. That tells us that b must equal 3, and so a has to equal 2. And we've found our partial fraction decomposition. So we knew that this was true. This is a true fact from algebra that you can do this, and we did a fair amount of work to find out what a and b were going to be, and now we can rewrite our integral as the integral of a over x plus 2, so that's 2 over x plus 2 dx, plus b, and b is 3 over x minus 1 dx. We're going to remember an important fact that we've seen before. So remember that the integral of 1 over x dx is a natural log of the absolute value of x plus c. This is because, think about, we're basically saying this is an antiderivative of this, and that would be true because if you think of taking the derivative of natural log of x, you will get this. We have to take absolute values because it's not legal to take a logarithm of any negative number. So you'll typically see this when we're taking an antiderivative, that you're going to have a log or a natural log of the absolute value of the expression. Okay, so this we're going to use over and over again with, we'll see them a lot in these partial fraction decompositions, because essentially here we could use a use substitution, but these ones are simple enough that we can probably just do it in our head. So first of all, let's take the 2, whoops, that's too big of an eraser. Let's take the 2 and put it out front. And then we'll take the 3 and put it out front. Okay, and so now when I look at this, and I want the antiderivative of 1 over x plus 2, that's just going to be the natural log of the absolute value of x plus 2. And so we have 2 times the natural log of x plus 2 plus 3 times the natural log of x minus 1 plus a constant. So let's convince ourselves that this is true. If I took the derivative of this, it would be 1 over x plus 2 times the derivative of what's inside, but the derivative of what's inside is just 1, plus 3 times 1 over x minus 1 times the derivative of what's inside. Again, the derivative of what's inside is just 1. So this is a very valid antiderivative. This is the solution to that integration. So again, we simplified this integrand by the process of partial fractions. We weren't able to integrate this before that, but once we split it up into smaller pieces, just separated out into simpler expressions, then these are integrals that we can handle pretty quickly. So this is the solution to the problem. Now this example is one of the more simpler ones that we'll see in the partial fraction world, because we have distinct linear factors in the denominator. So what do I mean by that? I mean that we have in the denominator, after it was factored, we have these 2 linear factors. So linear just means that the highest power on the variable is 1, and they're distinct, they're different. It is possible, we're going to see in some future examples, that a linear factor shows up twice in the factoring, and that has to be treated a little bit differently. It is also possible that instead of getting a linear factor, the factoring results in maybe a quadratic that's irreducible, and that has to be treated a little bit differently also. But this is the simplest case when we have distinct linear factors. And so this example shows how to find the partial fraction decomposition, and then how to use that to find the integral. So here is our next example of an integral we're asked to find the solution for. And the first thing that we have to ask is, does the method of partial fractions even apply here? We do have a polynomial over another polynomial, and the degree of this polynomial is smaller than the degree of this polynomial, so we're good. We can use partial fractions. So now we spend the bulk of our time over here finding out the partial fractions decomposition, and then we'll spend an itty-bitty amount of time finding the actual integral. So first we'll spend a little bit of time factoring the denominator. Right off the bat, I do note that as I look at this, I look to see if I can discover any factors that are just obvious. And if I plug in 0, that does not turn into a 0, so 0 is not a factor. If I plug in 1, I'd get 1 minus 1 minus 1 plus 1, and that actually is a factor. So we note that x equals 1 is not a factor, it's a 0 of the polynomial. So x equals 1 will produce a 0, we'll say, of the denominator. So x minus 1 is a factor of the denominator. Once I know that, I can do a little bit of polynomial long division to find the other factors. And so we have x cubed minus x squared minus x plus 1 And x squared will produce an x cubed minus x squared. That becomes a 0 minus x plus 1. And so that would be a minus 1 minus x plus 1. Okay, so it looks like this is where the other factors are. So we have 4x in the numerator, and in the denominator we have x minus 1. That one we just figured out by initially trying some easy numbers to see if they produced a 0. And then we were left with x squared minus 1, and the factorization of x squared minus 1 is just x plus 1, x minus 1. So then we have x plus 1, x minus 1. So we see that we have a repeated factor in the denominator. This is a new situation. So we're going to erase this guy, and we can just say that this is squared. When we have a repeated linear factor in the denominator, the partial fraction decomposition looks a little different. You have to repeat that linear factor in this way. So the x plus 1 just acts as it was. It's just a single linear factor. But if you have a repeated one, if you had a 2 or if you had a 3, 4, 5 potentially, then you have to build up to that with these simpler fractions for as many of those factors as you have. If we had a 3 here, we would have had x minus 1 squared, x minus 1 cubed, but we only have a squared, so we have these two. Okay, this is the structure for the partial fraction decomposition. And so we'll go ahead, as we did before, we'll multiply both sides by this denominator and sort of start clearing things out. And we have a 4x equals a times x minus 1, x plus 1, plus b times x plus 1, plus c times x minus 1 squared. And we multiply everything out. And we'll have a times, here we have x minus 1 times x plus 1, so that will just be an x squared minus 1, plus b times x plus 1, plus c times x minus 1 squared, so that will be x squared minus 2x plus 1. Okay, we're going to start collecting some terms. I'm going to look for all my x squared terms, and it looks like I have an a and a b. So on the left side stays the same, but here I have an a plus c times x squared. And then I start looking for my x terms. There's no x term here. There's 1 here, so bx minus 2xc. And so I can write plus b minus 2c times x. Those are all of the x terms. And then I look for my constant terms. I have a negative 1 times a. I have a b times 1 and a c times 1. And so my constant term will be negative a plus b plus c. On the left side, the only thing I have is an x term. So I have like a 0x squared plus 4x plus 0. So the x squared term should be equal to 0. That means that a plus c needs to equal 0. So a plus c equals 0. And then the x term, b minus 2c, needs to equal the x term coefficient over here. That's 4. So b, oh, you know what? I'm going to leave a little space since we're going to be solving systems of equations. So I have b minus 2c equals 4. That's just from the coefficients of the x term on the right and the coefficient of the x term on the left. And then I have no constant term over here. It's 0. And so this all has to equal 0 here. So negative a plus b plus c equals 0. Okay, so this is a 3 by 3 system of equations. So system of equations that we need to solve. 3 by 3 systems are slightly more complicated than 2 by 2 systems, but this one has some nice features. We know that a plus c equals 0. So right off the bat, we can say, okay, a equals negative c actually, and we can start substituting that in. Because of that, let's take that fact and put it into these two. So a equals negative c. Wherever there's a c, I'm just going to put a negative a. And so then I know that b minus 2c, and so that's plus 2a equals 4. And then I have a negative a plus b, and this will be another negative a equals 0. So b minus 2a equals 0. Okay, so again, this guy just came from this equation here where I replace the negative 2, I replace the c with a negative a, and then it became b plus 2a. I guess another way of saying that a equals negative c is to say that negative a equals c. So anytime I see a c, I can just plug in a negative a. Negative a plus b minus another a, so b minus 2a equals 0. Okay, so this system of equations is becoming easier and easier. I now know just by adding straight down that 2b equals 4. So b equals 2, and that means if b equals 2, that a equals 1. I just read that off of this one. b equals 2, so a would have to be 1, and that means that c equals negative 1. Okay, so I have found the pieces for my partial fraction decomposition, and all of this work was just to find that partial fraction decomposition. Now I'm going to go ahead and do the actual integral. So we'll split this page up and just do the integral, and the integral will be the integral of a, which is 1 over x minus 1, plus the integral of b, which is 2 over x minus 1 squared, plus the integral of negative 1, c over x plus 1. These integrals are pretty simple to evaluate, and we know that all of this is equal to this. So first off the bat, this looks like a natural log of x minus 1. So natural log of x minus 1. Just double checking. The derivative of this will be 1 over x minus 1 times the derivative of the inside. The derivative of the inside is just 1. And then I have a plus 2 times, okay, so this one I could use a use substitution, or I can just think through what's happening. This is like x minus 1 to the negative 2. This is just a power rule in reverse, so we're going to add 1, and that would be a 1 over x minus 1. That's probably all we need. If we think of the derivative of this, the 2 is just this 2. And then the derivative of this is x minus 1 to the negative 1, so that would come out front. Oh, it looks like we're going to need a negative. Okay, so the derivative of this will be x minus 1 will come out front. With this x minus 1, it's a plus. We have the 2, and the derivative of what's inside is 1. This power then becomes a negative 2. And that is what we started with here. So this is the true antiderivative here. So you may want to think through that just to convince yourself. Okay, and then we have this minus 1 and natural log of x plus 1 plus a constant. Don't really need the negative 1 right here, so we'll take that out. This is a fine way to write it. You may see the solution written a little bit different because of properties of natural logs. We can combine these. If you have a natural log of something minus a natural log of something else, then you can combine those into a division. So this is fine, but you can also simplify it by saying this is also equal to natural log of, it would be x minus 1 over x plus 1 minus 2 over x minus 1 plus c. So this also is a way that the solution could have been written. And that comes just from when you have a logarithm of the same base and the one's being subtracted from the other, you can combine it into one logarithm and then it's a division inside. That's a property of logarithms. And then this guy is just this guy and our constant. So this example was slightly more complicated than the last one because we had a repeated linear factor in the denominator. So this repeated factor in the denominator shows up right here. We had 2 of the x minus 1s. And because of that repeated denominator, the partial fraction decomposition works a little bit differently. You have to have 2 instances of it just building up to that repeated factor. And that will be true anytime you have a repeated linear factor in the denominator. So this was all the work that had to take place to get the rational function into a partial fraction decomposition. And our very first thing was we just tried to eyeball, what is a 0 of this polynomial, and there was a pretty basic one, just x equals 1 caused a 0. So we knew right off the bat that x minus 1 was a factor of the denominator. As soon as we knew that, we used polynomial long division to see if we could find the other factors. That popped right out, and x squared minus 1 is just x plus 1 times x minus 1. So we knew we had our three factors. One of them is repeated, the x minus 1 squared, and then we had the x plus 1. We did this partial fraction template for the decomposition, and then we multiplied both sides by that denominator, cleared everything out, and then we had a system of three equations with three unknowns that we had to solve, and that took a little bit of time, but because of how it was structured, it wasn't too difficult. We found our a, b, and c. Once we had that, the actual integration was fairly easy. We just had to remember to look out for when we had natural log antiderivatives and when we could just have a pretty simple reverse power rule. These all technically you could have used to use substitution, but because the derivatives of each of these was just 1 down here, we were able to mentally do this, find this antiderivative for each of these. The last thing we did was just combine these natural log terms into one natural log term. And so we have our solution. Next example is to find this integral here, and we have to ask, does the partial fraction method even apply here? And for it to apply, we need to have a polynomial over another polynomial. This is definitely a polynomial. This also would be, I mean, it is, and you could see it more clearly maybe if these were multiplied out, but this is definitely a polynomial. Okay, the next rule is this degree has to be smaller than this degree. So is this a problem here? Well, not really, because if we multiplied this out, we would actually get an x to the third term just by multiplying these guys. So the degree of the polynomial in the denominator is 3. That's larger than the degree of the polynomial in the numerator. So we're good on both counts, and so we can definitely do partial fractions here. This one is kind of nice because it's already, the denominator is already factored for us. The new thing here is we, instead of having a bunch of linear terms in the denominator like we have in the last two examples, we have this term here, which is a quadratic term, and it can't be factored anymore. If you tried to use the quadratic formula on it, you would see that in the real number system, this cannot be factored anymore. So this is called an irreducible quadratic factor, and when we have one of these, then things go a little bit differently. So this example is going to show what happens when we have an irreducible quadratic factor in our denominator. We're going to do some work now to find the partial fraction decomposition, and usually we just split it up into, we have one of the factors and then the other factor, and then we would have an a and a b on the top, right? We would usually write just a, b. When you have an irreducible quadratic factor, what you want to use is a linear factor on top. So the top will actually look like ax plus b. This is just a regular linear factor, so that's just a constant, and we'll use c there. But so this is kind of the new thing. If you have in your decomposition irreducible quadratic factor, then the numerator is not just going to be some constant like a or b. It's going to be a linear factor, ax plus b. Our goal still is to find what a, b, and c are, but in order to clear all these fractions, we're going to use a linear factor up here. And that will always be true, the thing that we try when we have that quadratic factor in the denominator. Okay, so let's go ahead and do that. We have ax plus b right here, and we have a c here. We'll do the same thing that we always do. We'll multiply both sides, by the denominator. So multiply both sides by this. The left side just cancels, and then on the right side, if we multiply both sides by that x squared plus 1 times x minus 2, this whole side, then this will cancel here and this will cancel on that one. So we're left with, on the left side, 2x squared minus x minus 1, and on the right side we have ax plus b, and then when we multiplied, this canceled with the x squared plus 1 on top, but we were left with this factor here, x minus 2. And then we have a c times, again, when we did the multiplication, the x minus 2's canceled, but we were left with an x squared plus 1. So x squared plus 1. All right, and now it's just multiplying out, matching up the different terms, and then we'll probably have a system of equations. So the left side's just going to hang out here, and on the right side I'm going to do a bunch of multiplications. So I'm going to multiply this by this, and this will be ax squared minus 2ax plus bx minus 2b. And then on the right side I have on the right side of the right side, I have plus cx squared plus c. And now it's just a matter of rearranging things and matching things up. On the left side, I have a 2 for my x squared term. I have a -1 for x and a -1 constant term. So we're going to collect all the terms in that order. Let's see, for the x squared terms, I have one right here, and I also have one right here. So 2x squared minus x minus 1 equals a plus c times x squared. And then for my x term, I have a -1 here. I'm actually going to just match up the negatives, the sign of how the x term starts. And so let's see, we have a 2a, and this will be a -b, and then there's no c term. So 2a minus b for x terms, and just double checking that I have to have a -2ax, that's right here, and then I would have a -bx, that's a positive bx, and that's right here. I just write the negative just so it kind of matches up with this negative, and then I can just say, oh, there's a 1, this must equal 1, but that comes a little bit later. Okay, what's left over is, again, I'm just going to match up the negative because of this negative, and we'll collect our constant terms. It looks like we have, no, here's a constant term, and here's a constant term. And so the constant terms will be 2b, and then we have a minus c. And just double checking this, -2b, and then we would have a plus c, and that's right here. Okay, so everything is as it should be, and now we're just going to match up the 2 needs to equal this, the 1 needs to equal this, and the 1 needs to equal this. And then we'll have our system of equations. So a plus c equals, actually let's move that over, just so we can line everything up. A plus c needs to equal 2, then 2a minus b needs to equal 1. That's coming from 2a minus b needs to equal the implied 1 that's right here. And last, 2b minus c needs to equal 1 as well. Okay, so I have this system of equations. I guess to solve this, I'll recognize that a, this relationship here, so a equals 2 minus c, and then whenever I have an a, I'm going to put that in, and then I'll use these two equations here. I'll put everything in terms of b and c. So 2a is just 2 times 2 minus c minus b equals 1, and that means that because of that, negative b, and then I have a minus 2c equals, I have a 1 over on the right side, and I'll have a 4 over here. If I take the 4 over, 1 minus 4 will be a -3. Okay, so all of that just came from this second equation once I used this substitution for a. I do that so that I can, now the third equation says 2b minus c equals 1. And then we will take these guys right here and solve for b and c. I'm going to multiply the top left and right sides by 2. And so I have a -2b minus 4c equals -6. And then this equation right here is just, I'll bring that along, 2b minus c equals 1, and add straight down so that I get 0 b's, but I have a minus 5c equals -5. Okay, so I know now that c equals 1, and that means that a equals 2 minus 1, so a equals 1. And so then I can use this 2a, which is 2, minus b equals 1, so that means that b equals 1. Okay, so this is, these are all the pieces I need to rewrite my rational function as a combination of simpler rational functions. And so my equation, or my integral, becomes the integral of ax plus b, and that's x plus 1. So this was just the ax plus b, x plus 1 over the x squared plus 1. And then I have the integral of c, which is 1 over x minus 2 dx. Okay, so hopefully this will be simpler to evaluate than this guy. And it will be. This one is piece of cake like we've seen before. It'll end up being a natural log of x minus 2. This one, we look at it and we think, okay, how are we going to integrate this? A u substitution won't really work because if we let this equal u, then du is just 2u, but we have kind of left over this x plus 1. We have seen an example like this a few sections ago where the best path forward is actually just to split this up into two fractions, an x over x squared plus 1 and a 1 over x squared plus 1. If we do it that way, this first fraction does lend itself well to a u substitution, and then this one, the antiderivative of 1 over x squared plus 1, we recognize that this is going to be actually arctan. So this is one that we remember the antiderivative of. So that's what we're going to do. We're going to split this guy up into x over x squared plus 1, and then we have a 1 over x squared plus 1, and then we still have our 1 over x minus 2. Okay, so I'm going to use a u substitution on this first one. I'll let u equal x squared plus 1. The reason I immediately recognize this is because now the derivative of this will be 2x, and I have that important x part of that right there. So du equals 2x dx. And so I really have the integral of u right here, and du, I'm going to have a 1/2. This integral, so just convince yourself that this is what you're getting after you make the substitution. We have the u, and then x dx we have, and then this 2 we need to move over here, so we have a 1/2 du. This is just going to be a natural log, our arctan, and another natural log. So all of the pieces are coming together. So we're going to have the natural log of u, which is the natural log of x squared plus 1, and we have a 1/2 in front, plus arctan of x, that's just coming from this. The derivative of arctan is 1 over x squared plus 1, so this is the right antiderivative, plus natural log of x minus 2, plus a constant. So we do have our solution. Let's just review again what made this a little bit different. The really different thing was that we had this irreducible quadratic factor in the denominator. When we do have that, then in our partial fraction decomposition, the numerator needs to look a little different. Because we had this guy, we want to use this linear template for our partial fraction decomposition. This is as far as we're going to go. You can actually get irreducible quadratic factors when you have a repeated one. That's a whole different process. You could probably guess how that goes, but we're going to stop here. So the 3 examples we've seen so far, these were the 3 cases we saw. The easiest was where we had distinct linear factors in our decomposition when we factored the denominator, and that's pretty straightforward. It just works like this. And then the second example, we had a repeated linear factor right here, and when we do, we have to treat that a little bit differently. You have to build up to it in your partial fraction decomposition. You have to have one that represents the linear one, and then you have another one that represents the quadratic, or the repeated one. And our last example was where we had an irreducible quadratic. This guy cannot be factored anymore, and so when that happens, your numerator looks like this. There is one more case where you would have a repeated irreducible quadratic. We don't go through it. We're just going to stop here. But those are the only 4 cases when you're doing partial fraction decomposition, because you're guaranteed to either have in the denominator linear factors or quadratic factors. You won't go any higher than that ever. And so because of that, there were only the 4 cases. The 4th case we leave off, but these ones we want to be able to know how to do this decomposition. Once we do the decomposition, the integrals aren't too bad. We ran into a lot of natural logs of things. We did run into a reverse power rule. I think we had a 1 over, I can't remember exactly. Oh yeah, in this second example, we had this well, it's really 2 over x minus 1 squared. This was just a reverse power rule with a kind of mental use substitution. So a lot of natural logs, we did have this reverse power rule. And then in the last example, we had an antiderivative that ended up being arctan. So for sure your bread and butter are going to be the natural logs, but look out for maybe a possible arctan or a reverse power rule as well.